Hello, my name is Maggie Welch, and today I'll be talking about electrolocation, and I'll be doing some practice problems. First, let's discuss the difference between ampullary receptors and tuberous receptors. Ampullary receptors detect low frequencies like heartbeats, so they're best for passive electrolocation. Tuberous receptors detect higher frequencies, so they're used for active electrolocation. Tuberous receptors, as you can see in the image here, have an epithelial plug that acts as a high frequency filter. It also has a shorter channel than the ampullary receptor, which is seen on the left. They both have a mucopolysaccharide gel in the channel, which is highly conductive, so the frequency of the emitted signal from the prey is the same from the outside of the receptor to the inside of the receptor, where you can see the sensory cells will pick up the electrical signal. Now let's discuss the difference between freshwater and saltwater in terms of electrocytes. In freshwater, the electrocytes must be stimulated simultaneously in order to get the full output, and they are arranged in series, which is what you can see right here. The electrocytes generate action potentials via sodium current coming through voltage-gated sodium channels. In salt water, the electrocytes are arranged in parallel, which is what you can see right here. The electrocytes generate excitatory junctional potential via acetylcholine nicotinic receptors, which conduct sodium and calcium. So electrocytes in salt water are not voltage dependent. So our first practice problem is assuming that the main electric organ of the electric eel consists of 28 stacks connected in parallel, containing 6,000 electrocytes connected in series, and each stack that has a reversal potential for sodium and potassium ion currents of positive 50 millivolts and negative 80 millivolts, respectively. Estimate the maximum potential difference generated by the electric eel at the electric discharge. For this problem, we have to remember that parallel circuits, you have to add current, and for series circuits, you add voltage. So to calculate this, we're going to add the absolute value of the ion currents, so that's 50 plus 80 equals 130, and then we're going to multiply by the number of electrocytes. So we're going to look at this number, so 6,000 electrocytes, and not look at the fact that there's 28 stacks. So it's 130 times 6,000 equals 780,000 millivolts, or 780 volts would be the answer here. Our second and final practice problem is if an electric organ of an eel produces 600 voltage and 1.1 amps of current, what is the electric power of the electric pulse? So for this, we're going to use the power formula. So that is power equals current times voltage. Our current will be 1.1 amps and our voltage is 600 volts. And that will result in 660 watts. So this electric organ is going to produce 660 watts of power.